Welcome to the Explainer. When we look at the absolutely incredible leaps AI is making right now, whether it's generating hyper-realistic video or writing complex code, it is so easy to just focus on those massive, ultra-fast processors doing all the heavy lifting. But here's the thing, the biggest, most critical race in AI right now, it's actually not about the processor at all. It's about a hidden superhighway sitting right next to it. So what happens when the fastest GPU in the world gets hungry? Picture this, you just got your hands on the world's absolute fastest, most bleeding-edge GPU. You plug it in, fully expecting it to just revolutionize your AI models. But then a glaring problem pops up. What exactly happens when that processor gets exceptionally hungry for data, but the kitchen is just way too far away? Well, this scenario is basically the central villain of our story today. Our world's most powerful, incredibly expensive AI chips are actually starving. 50%. Yeah, you might be totally shocked to discover that your top-tier processor actually spends a staggering 50% of its time just sitting idle. It is literally doing nothing, just twiddling its thumbs, waiting for data and memory to arrive from across the circuit board. It's kind of like buying a Formula One race car and then spending half your dime stuck at a red light. This starvation has become the single biggest challenge and honestly a massive bottleneck in modern AI development.
Okay, let's dive into this. Section 1. The AI memory bottleneck. Let's see exactly why our systems are constantly waiting for data and what's holding back the next generation of AI. To really wrap our heads around the problem, we have to look at the physical layout of traditional computers. In a standard setup, you've got DDR memory, and it's usually sitting several centimeters away from the CPU. Now, gaming GPUs improve on this a bit by using GDDR memory, placed closer around the graphics chip. And hey, while those solutions work perfectly fine for regular tasks in video games, AI is a totally different beast. Training an AI model requires moving absolutely massive datasets, back and forth, constantly. When you're forcing all that data over those physical distances, traveling through tiny copper traces built into a traditional motherboard, it creates an unacceptable amount of delay. Those copper traces basically act like a narrow country road trying to support a massive fleet of semi-trucks. So the solution here isn't simply building faster GPUs. We have to build much, much faster memory.
Which brings us to Section 2, Anatomy of HBM, and how vertical stacking becomes the hero of our story by fundamentally bridging this physical gap.
Enter HBM, or high bandwidth memory. Instead of laying memory chips flat on a board centimeters away, HBM takes those chips and literally stacks them vertically. Then it drops that stack right next to the processor on something called a silicon interposer. Now, this interposer isn't just some basic piece of plastic, right? It's a highly complex, precision-engineered piece of silicon that acts like a microscopic communications bridge between the processor and the memory. By using it, data doesn't have to travel those long, inefficient distances across a standard motherboard anymore. Instead, it moves just a few millimeters. Shrinking that travel distance down to mere millimeters is the real magic trick here. It creates absolutely massive data bandwidth while simultaneously lowering overall power consumption.
And this brilliantly illustrates the whole concept. I actually love the source materials analogy of a stack of pancakes for this. Think of each pancake as one DRM memory chip. To get data rapidly through that stack, there are these tiny vertical electrical connections called through-silicon vias, or TSVs. Imagine them like microscopic toothpicks, piercing all the way down through every single layer of your pancake stack. All of these vertically stacked memory layers sit on a base logic die right at the bottom, which acts like a traffic cop, managing the data flow. Finally, that entire stacked assembly, the whole shebang, is placed right next to the GPU on that silicon interposer we just talked about. This ingenious architecture creates thousands of ultra-short, high-speed data connections. Compared to conventional setups, you're getting dramatically increased data transfer speeds while using substantially less energy.
Now, let's look at Section 3, HBM3E versus HBM4. We're currently moving into the 6th generation of this technology with HBM4, and trust me, this represents way more than just a simple speed bump.
Unlike previous generations that kind of just tweaked the clock speeds and called it a day, HBM4 represents a fundamental redesign of the memory interface itself. Let's compare it to its predecessor, HBM3E, which is honestly excellent for today's AI chips. HBM3E uses a 1024-bit interface and delivers up to about 1.3 terabytes per second of bandwidth. But look at HBM4. It completely doubles the interface width to 2048 bits. It pushes the channel count from 16 up to 32. And the bandwidth? It blows past 2 terabytes per second per memory stack, with some advanced implementations expected to hit over 3 terabytes per second. Crazy, right? On top of that, these structural changes allow individual stack capacities to reach an astounding 64 gigabytes. In practical terms, that higher capacity means you can load entire, massive layers of a large language model directly into the fastest memory available without having to constantly swap data out to slower storage. It drastically reduces those bottlenecks. HBM4 is truly built from the ground up for next-generation AI accelerators.
Industry experts have a really great way of phrasing this. Think of it like upgrading from a 4-lane highway to an 8-lane superhighway. By literally doubling the physical lanes, the number of cars, or in our case, the amount of complex data, moving every single second increases dramatically. This upgraded 8-lane superhighway allows AI accelerators to feed enormous amounts of data to thousands of processing cores simultaneously without experiencing a single traffic jam.
So let's shift our focus to Section 4, why AI needs HBM4. Let's look at the intense logistical challenges of feeding these processor cores in the real world. The reality is that modern AI models have grown at an exponential, dizzying rate. We're talking about models containing hundreds of billions or even trillions of parameters. Training models of this immense scale requires moving enormous datasets every single microsecond. Without the massive memory bandwidth provided by HBM4, we hit some really severe consequences. GPUs end up constantly waiting for data, and incredibly expensive hardware just sits there idle. And because of this downtime, training the AI takes way longer, which means energy consumption shoots straight through the roof. HBM4 significantly reduces this memory bottleneck. So instead of starving the GPU, it keeps thousands of AI cores continuously supplied with the data they crave.
So you might be asking, who is actually building this critical infrastructure? Well, this vital production is led by just 3 major companies, SK Hynix, Samsung, and Micron. These 3 titans supply the memory for the cutting-edge AI accelerators used by giants like NVIDIA and AMD. Right now, industry shipments and manufacturing operations at these 3 companies are ramping up aggressively just to try and meet the immense, seemingly insatiating demand of next-generation AI platforms. Now, you might be wondering when you can get HBM4 in your own computer at home. To be completely clear, you are not going to find HBM4 in your living room or your standard gaming PC anytime soon. It's just extremely expensive to produce. It requires highly advanced packaging, those specialized precision silicon interposers we talked about earlier, incredibly complex manufacturing lines, and very high-end liquid cooling systems. Instead, you'll find it exclusively inside AI supercomputers, massive cloud data centers, scientific computing clusters, and advanced large language model servers. Consumer GPUs will just keep using traditional GDDR memory because it remains much, much cheaper, and honestly, it is perfectly adequate for everyday tasks and gaming.
Let's transition to Section 5, the future of AI memory, and ask, what's next? It is genuinely fascinating to see how these microscopic structures will shape our macroscopic world.
So the crucial point here is that memory technology is evolving faster than ever before. As AI models continue their relentless exponential growth, future generations of HBM will absolutely have to keep pace. We can expect even larger capacities, higher and higher bandwidth, and even better energy efficiency. But perhaps most intriguingly, we can expect smarter logic to be integrated directly into the memory stack itself. This concept, often called processing in memory, means that the memory might actually do some of the foundational math before it even sends the data over to the GPU. By handling basic computations locally right there within the memory stack, it saves an immense amount of transfer time and energy, basically blurring the lines between just storing data and actively processing it. It's a real game changer.
And this brings us right back to our core thesis today. The race is no longer just about building faster processors and GPUs. It is equally about delivering data to those GPUs as quickly and efficiently as possible. From the advanced chatbots we use daily, like ChatGPT, to the autonomous vehicles navigating our streets, and even vital scientific research curing diseases, memory bandwidth has proven to be just as absolutely crucial as raw computational power. HBM4 is so much more than just a simple memory upgrade. It really is the key that unlocks the next generation of artificial intelligence. It's the hidden backbone making all of these incredible software leaps possible. Which leaves us with one final exciting question to ponder. As this memory technology continues to scale and evolve, how much faster can we feed the brains of tomorrow's technology? Thank you so much for joining me for this explainer. Keep wondering, keep learning, and I'll catch you next time.